Today we are going to discuss one of the important topic of circuit analysis, which is actually current divider rule and the use of the nodal analysis. And before I start discussing about these things, once again I want to say something about the circuit analysis so that those students who may be trying to see this topic directly, when they know that they have to know about the circuit analysis, they would be interested in the definition of the circuit analysis. I want to tell you that first of all, what does the circuit means by itself? The circuit is actually any electrical elements when they are connected together, and definitely we need some kind of source to run those circuit elements, and together those, when put together in some sort of a circuit, in some sort of a combination, in some sort of a configuration, that is called actually a circuit. And if we want to find out how much any element requires the consumption of the current or the voltage, these values, if we can determine, then and if we can find these values for all the elements connected in a configuration in a circuit, this means is actually circuit analysis. So today our topic is the current divider rule. First of all, what is current divider rule actually? When we know that for any circuit, for example, this is a circuit we have today. We are going to solve it as well. In this circuit, you see that we have the resistors and the current sources connected together in a particular configuration, and these current sources are sharing their currents with these 1, 2, 3 and 4 circuit resistors elements. So they are sharing, they are dividing the current. So the division of the current within the circuit elements is as according to some rules and regulations. So that is the current divider, and we use the current divider rule for that purpose. And to solve this according to the current divider rule, first we will bring this circuit into a simplest form. So the first step is actually to bring this circuit into the simplest form. And as according to the circuit analysis, we want to find out the currents and the voltage against all the elements. But in this circuit, we are only requested to find out the current against this resistor, or this resistor is given a particular name of load resistor, and the rest of the resistors are just shown as it is. So we are only interested to find the current in this one. So to find the current in this one, first we have to simplify it. For example, how to simplify, how we can simplify it? Just for the sake of simplicity, we can connect one, 2 and 3. All these 3 resistors, 9 kilo ohm, and this one is 12 kilo ohm. So after putting these resistors together in the parallel configuration, and now we are putting the current sources together. This is 1 milliampere, and the next one is 4 milliampere, and the final one is 2 milliampere, and this resistor I have kept deliberately separate because we cannot remove this one, since we have to find out the current in this load resistor. Now the question arises, some of you may think that, sir, how can you actually bring all the resistors from within the circuits to one side and similarly the currents together? Actually, for this you need to find out and know, actually, once you start from this point, let's say you starts moving, and when you reach here, you see it's another node, but there is no element coming in between it. and then further you start moving, and then this is another point where the current is being divided, and then you keep on moving, and then you reach to this point, and then similarly you keep on moving, and you see that if you pick it up from here and bring it here and take it back, actually this all remains as a single same node. So you can give that this all makes up a single node. There is no second node appearing over there. So that's why we can simply take them forward or backward as per our need. Similarly, in the ground, you see there is nothing actually. There is the same situation on the ground side. So you can also put a ground here. So it's actually the same. There is only one node also in the bottom. So in this kind of situation, you can take any element forward or backward. So no problem. So that's what we have did actually here. So now we have to simplify this portion. We need to find the equivalent resistance plus 1 over 12 kilo ohm, and this is 1 over, let's say R parallel. You can give any name, RA, R1, R anything. To simplify this one, we actually, you can take the LCM, 36 kilo ohm, and this is 2, 4, 3. So this is actually 9 over 36 kilo, 1 over Rp, or Rp is actually 36K over 9, which is 4 kilo ohm. So we have the resistance for all of these elements together, and for this portion we can apply the Kirchhoff's current law. We can apply the Kirchhoff's current law. Kirchhoff's current law. According to the Kirchhoff's current law, the sum of currents at any node is equal to 0. Means sum of current where, let's say, I is equal to n is equal to 1 to n, or you can give it actually R is equal to 0. So applying this one at this, only at this portion, we are not talking about the whole portion. After having solved this one, we will also solve it with the nodal analysis, and there we will actually apply the Kirchhoff's current law, and then there we will see then we will apply the Kirchhoff's law on the whole circuit. But for the moment we are actually focusing on the current divider rule. So we have to solve this question according to the current divider rule. So for that purpose we are simplifying the circuit, and this portion is simplified this way, and this portion is going to be simplified according to this one. And actually you can also write directly. You see, this one is 1 milliampere, this one is 4 milliampere going downward direction, this 2 milliampere, this 2 and this one are both going up. So 2 plus 1 is 3 milliamperes going in the upward direction, and then you see this is 4 milliamperes going in the downward direction equal to 0. So if I remove these arrows, or I remove one of the arrows, let's say we can take this one. This one is actually originally you see this current is coming 1 milliamperes from here, 2 milliamperes from here. So these together are 3 milliampere in the upward direction, and this 4 milliampere is in the downward direction. So I want to now solve this one. You see this current is in the upward direction and this current is in the downward direction. So if I want to change this one to the downward, so this will become 3 milliampere in the downward direction, but we will have to place a minus sign for changing the direction. And here this is already in the downward direction, so this becomes equal to 0 is the same. So if now you can solve this one, because this and this one are in the same direction, so this is 1 milliampere in the downward direction. Okay, so this is the solution. So what is left is this current. So for this whole circuit we will have 1 milliampere in the downward direction. So now we have to make this circuit once again. So here we can make it for all these three resistors. We will make only one resistance, but its name will be now Rp, which is equal to 4 kilo ohm. Once again, this P has to do nothing. This is nothing technical. This is only a P, a given name that for the parallel combination we have put a P for parallel. You can give it a name of 1, 2, 3 or whatever, or even you can keep it just R as you wish. The next is the current source, which actually you can also, okay, let's keep it in the middle. This is in the downward direction. This is 1 milliampere. And our load resistor RL is equal to 12 kilo ohm. This one 12 kilo ohm. And we have to actually find the IL is here. Yes, here we have reached the point where we can apply the current divider rule. According to the current divider rule, when you have to find the current in any branch, okay, before solving it, just to make it clear, you see that again this is all the elements are in the parallel configuration, and when you start from here to this till this point, you find nothing in between except there is a point of division, and all this to configure grades one node. Similarly on the ground side is the same situation, and we can also again we can make it in this form as well. So just to why I'm doing it, since this is a kind of lecture for the guys who are just very new to the topic, so that's why I'm going and telling almost everything so that they don't get confused. And you can place the same circuit, you can also write in this fashion. It's just the same, using the same philosophy that we used here actually, from coming from this point to here. And here this is 4 kilo ohm and this one is 12 kilo ohm, and this is actually IL, and this is actually our RL, and this is actually we gave the name RP. Okay, so this is now, and according to the current divider rule, okay, we can actually now erase this one, and we also don't need it, though we will need it, we will write it again. Okay, so from this circuit now we have to apply the current according to, you can write according to current divider rule. The derivation of the current divider rule is given in a separate video. It's a very little, very small, coming directly being derived directly from the Kirchhoff's the Ohm's law. And but here we will just simply apply according to the current divider rule. When we have to find the current in any branch connected in parallel, since we have to find the current in this branch, we will not write the resistance of this element, rather we will write the opposite, and the opposite one is Rp divided by total resistance of the whole circuit, you can say, or actually this is I. You can say, if you want to give it name of I source now, for example, let's say this is I source at the moment. So this is your I source. Just we have given a name to the current source, I source. So we will now find the Rp is 4 kilo ohm divided by total or sum of the all resistances actually 4 kilo ohm plus R is 12 kilo ohm into I source is 1 milliamperes. You can easily see that this kilo and this kilo is common from this, and kilo is common from this. Kilo will be cancelled out, up and down, and what we will be left is 4 divided by 16 into 1 milliamperes for the 16. So this is actually 1 over 4 milliampere. However, there is something to be noticed. This current is actually opposite to this current. This current source is representing that this is going downward at the moment. This current is going downward, but this current is also going downward. So how this current can enter this one? So this current is actually entering from this path, which means if it is coming from the ground point, it means there must be an opposite sign. Or if you feel it difficult to solve this way, you can do another thing. And what is that? You can actually here or here, where if you change its direction from downwards to upwards, it means you will have to place a negative sign here. Just like the similar philosophy of this, you see here 2 and plus 1, 3 minus 4, so this becomes minus 1 as well. Okay? If we keep the direction upwards, because this is downward. So this is actually the similar way. You can also do it this way or that way, it's the same. If you do it this way, then actually the minus will automatically appear here. In this formula, once you will place the values, it will automatically be coming here, and you will not have to actually, just for the sake of clearance, let's keep it simple. You see here for the 16 and minus 1 over 4 milliampere. Either you can, if we would be solving in the similar manner as we were solving for this one, then you would have to write a statement that both the currents are going in the opposite direction, and you will have to place a negative sign over there. But if you don't want to write any statement, then you will have to change its direction upward, and you will have to place a negative sign. And now if you solve, you will automatically get a negative sign over there. But it is your choice. It's up to you. Whatever the way you want to solve it, you can solve it, but you must make sure that you do not mess up with the directions and you do any mistake. And I have done both the cases, and by this way you can actually solve this, and you have now your required result, I is equal to minus 1 over 4 milliampere. So this is our solution. And if the questionnaire, if you are asked to find the VL as well, it's too simple now. VL is equal to, actually V is equal to IR. So IL into RL.